Hi again, so this video now is on 8E, looking at modelling geometric growth and decay. Remember 8C, we were looking at linear growth and decay, so that's when the growth was occurring in a straight line because the same amount was added on. But this time, geometric growth or decay occurs when an amount increases or decreases by the same percentage in regular intervals. So it means that the amount will change because it's increasing at a percentage rate. This is classical example on compound interest and if a car is depreciating at a constant percentage per year. So we're going to talk about both of those examples. Now, compound interest, you might remember from last year, this is the one that I called interest on interest because if you get to the end of the year and you've earned $100 in interest, then for year 2, your interest is calculated on that initial principal plus the $100 that you've earned. So you start to accrue more and more interest over time, which is great for us if we're saving money in a bank, but terrible for us if it's, say, a loan and we're having to pay even more money on the interest already accrued over time. Now, in terms of this recurrence model for compound interest, we have here that the VO is the principal, which we already know, and then the rule is Vn plus 1 equals R times Vn. So R stands for 1 plus R over 100 here. And that's because 1 represents 100%, so 100% of the initial amount, plus R over 100, so that percentage interest that's found in a compound period. So if we look down here at an example, it's got that Tanya borrows $8,000 from the bank and the bank charges interest of 4.5% per annum. Now it says here, write down a recurrence relation to model the value of the loan if interest is compounded yearly and also if interest is compounded monthly. So one thing I'll say is interest rates are always given to us as per annum, okay? And we know that our VO here is $8,000. So if we look at VO, So VO is $8,000, okay? And then Vn plus 1 equals 1 plus 4.5 over 100 times Vn. Now, we can actually simplify that bracket there. So remember, if we've got 4.5 over 100, that can actually be written as 0.045. So we could actually write this here as 1.045 Vn, which is definitely a lot nicer to look at. And what that's doing is because that number is greater than 1, we can see that it is slightly increasing the value of the previous, slightly increasing the value each time we're compounding the interest there. Now, if we had to do this for B, where it says to compound it monthly, remember I said before that interest rate is 4.5% per annum. So we actually need to work out what that rate is in terms of a monthly rate. So we need to take 4.5 and divide it by 12. Now, if I do that, so in my calculator, 4.5 divided by 12, that becomes 0.375. So 0.375%. So now when I write my rule, I've got VO is $8,000. And Vn plus 1 equals, now I'm going to add this onto 1 straight away, but remember I've still got to divide this by 100, which means I've got to move this decimal point another 2 spots back. So it's going to be 1.00375 Vn. So they are my 2 rules depending on compounding yearly or monthly. Now part B, it says, should Tanya pick the yearly or monthly compounding option? Remember here with interest, she is borrowing money from the bank. Borrowing. So she wants to pay as little interest as possible, which means in this case, she should pick the yearly compounding option because then her interest is only compounding at the end of the year. But if she was picking the monthly option, then every single month a little bit of interest gets added on, and then the next month gets calculated plus that little bit extra. So that would be really great if she was saving money, but if she's borrowing money, she wants to take the yearly option. So we're going to say yearly because she has borrowed the money and wants less compounds. Now, C, it says, if Tanya picks the yearly option, how much will she owe the bank after 1, 2, 3 years? So let's write down 1, 2, 3. And again, we're going to head to our calculator here. I can work this out. So 8,000, I can type that in and then put in times 1.045 and press enter. So at the end of first year, it's going to be 8,360. And now if I press it again, end of second year is 873620. And a final time, 9129.33. Now, a couple of things. All of these need dollar signs, so we're dealing with money. We always need dollar signs. And our second thing, we're dealing with money, we always round to 2 decimal places. So a finance question is, unless it says the nearest dollar, it's otherwise not going to tell you what to round it to. You always round it to 2 decimal places because there's 100 cents to the dollar. So every single time without doubt there, that's why that third one became 9129.33. Now part D, it says create a graph of the information from C. Let's do this on our calculator and move it over because it's going to be more accurate. So again, statistics menu, 0, 1, 3, let's just delete these other years. And so originally it was worth $8,000. At year 1 it was 8,360, 8736.2 and 9129.33. Now again, if I go set graph, I'm just going to make this a scatter this time. If I look at this, it's a bit hard to see it with this on this such small scale because this graph on my computer has zoomed it in for us. But what we will start to see is these graphs won't be making a direct straight line anymore because they are geometric growth. So I'm just going to draw a picture here of what sort of shape we'll start to see. We'll start to see ones that curve like this because it's going to start increasing quite rapidly. So that's what's going to start to happen, that if we've got years down here and dollar value up there, it'll start to increase more rapidly. Now, if we depreciation, in terms of geometric decay, we have what's called reducing balance depreciation. And it's saying that each year the value is reduced by a percentage of the previous year's value. So this is really similar to that compound interest where we were adding on a percentage each year, but this has decay rather than growth. So we are, in terms of our R value, using 1 minus R over 100 here. So this also means that when we write these before, like we had 1 plus 4.5 over 100, and remember that became 1.045. If we did that and we had 1 minus, let's just say 5 over 100, that's like saying 1 minus 0.05, which would become 0.95. So this time our decimals that we're using are going to be between 0 and 1 because they are then shrinking that number down there, being smaller than 1. So if we look at this example here, we've got the following recurrence relation can be used to model the depreciating value of a new car. It says VO equals 40,000, VN plus 1 equals 0.88 of VN. Part A wants what is the initial price of the car. Remember, that's always our VO value, so it is worth $40,000. And part B wants to know what is the rate of depreciation of the car. So the R value that we're using here is 0.88, and we want to know how much smaller that is than 1. So if we do 1 minus 0.88, that gives us 0.12. To make that a percentage, we need to times it by 100. So we've got 12%. So the car is depreciating at a rate of 12% there per annum. Now it says use the recurrence relation to find the value of the car after 1, 2, and 3 years. So let's write down 1, 2, 3. And if I go back to my main menu of my calculator here, and I can put in 40,000 as the initial amount and times 0.88, enter. At the end of the first year, it's worth $35,200. At the end of the second year, it's worth $30,976. And the end of that third year, it's worth $27,258.88. Okay, so we can see that each year it is decreasing in value, but it's not decreasing by the same amount there. It's slowly, changing how much it is decreasing by, because we're decreasing by a percentage and not a flat rate. Now, part D, it says create a graph of the information from C. So let's set up some axes here for us, and this is car value in dollars. So let's put 40,000, 20,000, 30,000, 10,000. And down the bottom here, 0, 1, 2, 3. So this is time in years. Remember, initially the car was worth 40,000, so we'll put across there. At the end of the first year, 35,200, so that's in there. Then 39,76, so maybe in there. And then 27, so a little higher in there. And so what we can see then is this is starting to curve downwards here, okay? So we don't have a straight line like we had before, but it is starting to create a subtle curve for us that the car is decaying in value by. That is 8E for you. The next chapter is 8F, and that is going to look at creating the nth rule for these compound interest and reducing balance depreciation. So please flick to that video to continue with chapter 8.